Next talk is by Jack Barth, using underwater robotic gliders to explore and understand our planet ocean.
So I want to thank Larry and the rest of the steering committee for this honor to be able to talk at this symposium. What a great chance to be able to honor our father. And I really want to say that, you know, our dad didn't bring home his papers and sit us down at the kitchen table and go through things, right? He led by example, like he did for many of you. He told us about the cool science occasionally. He dragged us into the lab, and we played the first Star Wars game on the PDP-11s. we got to tie rubber hoses into knots and put them in the liquid nitrogen and hit them with hammers. And so, you know, he inspired us to think about science. So I just want to tell you about a little bit about what I work on. It's completely different from you guys. I'm going to talk about the planet ocean. But first I'm going to do another thing that our dad was very famous for, and that's the Charlie Barth quiz. So he would always come up with some question that he'd want you to think about. And spouses were not immune. So this is an easy one, but we're going to use the answer later. So I need somebody out there to tell me how far around planet Earth is in kilometers.
40K.
40,000. So hang on to that one. So Dad dragged us down to White Sands, and we got to see sounding rockets go off. So I got a chance to repay him by dragging him out on a research vessel in 1997. And after 12 hours of being sick down below, he popped up and was really involved in the things we were doing on the fantail. The other thing is Dad always worked with students, and we've all taken that away. This is a student of mine from Senegal that's interested in the ocean and how that works. So why do we care about this? This is the color of our planet. These are plankton growing in the ocean. You see most of the ocean is a desert, but along the coastlines and at the high latitudes, that's where a lot of the production is. In fact, those areas are 1% of the surface area, but it's 25% of the wild-caught fish. So if you enjoyed your lunch today with a little bit of fish, 1 billion people get their primary protein from fish. So I get to put on a set of equations. These are the shallow water equations. They tell us how the fluid moves when you push on it with the wind. So in the bottom left diagram is a little way that the coastal ocean works. The wind blows, the surface goes downwind, but because the Earth's rotating that Coriolis parameter F, it spins off to the right near the coast. It leaves a hole in the ocean that can only be filled by cold water from below. That water has nutrients in it. It stimulates plankton into the light zone, and we get this amazing fishery. And you can see a satellite image on the right-hand side of sea surface temperature, that cold water along the coast. It also comes with low dissolved oxygen, which I'll explain now. So as the water sinks into the ocean, it does that at high latitudes. In fact, the water off Oregon comes from northeast of Japan. It's cold enough to sink and get dense, and it slides down, and for about 10 to 40 years it travels across the Pacific till it gets down off our coast and is upwelled by that process I just told you about. Along that path it loses oxygen and it gains CO2. And as you've been reading in the news, that's what drives the pH down. It's then upwelled onto the coast where it affects our ecosystems. So we've been launching these missions to study planet ocean. These are underwater robots that we can send out for months to a half a year at a time. They're about as tall as I am. They're autonomous. We can use them to explore the planet ocean. Here's me standing with one of them on the dock. And you probably see something missing on here. There's no propeller. Okay, and this was the key to go from a very fast, low-endurance vehicle, something that would last one day, to something that could last a half a year. No propeller, so we drive it through changes in buoyancy. It's just a cylinder that we have a piston that goes in and out, changes the volume, it can go up and down. And the wings on the side cause a very gentle glide through the ocean, hence the name underwater gliders. And we do things like you guys do. I saw those payloads being ejected out to the side with some kind of mechanical contraction. We actually use something called pitch batteries up here in the nose. They're a cylindrical cone of C cells. There's 250 C cells that drive this. We go a half a knot of speed, and we do that at half a watt. So it's half a knot at half a watt. To pitch down, we drive that pitch battery forward. Dip the nose down, pull in the piston, and down we go. So it's like the guys in the World War II submarines, right? Running to the front of the submarine and pitch down. The real breakthrough was the ability to do GPS and to call home via the Iridium satellite phone. And so because there's a global constellation, we can do this basically anywhere on the planet. So we measure temperature, salinity, chlorophyll, the velocity of the water, and importantly, the dissolved oxygen. So our dad, as we've heard, worked with many students. Alan Dennis in our lab worked on this actually when he was in high school. And he learned how to use these 3D visualization systems. So he made this for us about how the glider flies underneath. We detect the bottom with sound, so we can turn back up. We're flashing light looking for chlorophyll. We're actually using an optical oxygen quenching technique to look at oxygen. We surface every 6 hours and phone home. And the cool thing is I can pilot it from here. And the students can pilot it from here. So I was really intrigued by that 10-week training program. We take about 10 minutes and we and we can deploy these from all over the place, various vessels. There I am in a rowboat off Chile, dumping one of these things in. And the question is, why haven't we been doing this for 40 years? And the answer is small form factor computers, flash memory driven by the consumer electronics, GPS, and the Iridium. That's all come together to allow us to do this. So we've been flying these off Oregon. Here's our drunken paths trying to stay on one line. And the reason we're not on that line is because there's ocean currents that are greater than half a knot, literally pushing us around. So for about almost coming up on a decade, we've had these in the water about 4,000 days. We've contributed 250,000 profiles. So I know you guys, satellites, create profiles all through the atmosphere. These are going from the surface to the bottom and back up. For comparison, in the previous 50 years, there were 4,000 profiles. So now this is a revolutionary way to look at the ocean. So we've gone for 86,000 kilometers. So that's where we have to use the answer to the quiz, twice around the planet. Okay, so what have we learned? This is the kind of the payoff figure. So the coast is on the right, out into the deep ocean. I've just done color along the track of the glider for the oxygen content. Red is good, lots of oxygen. Blue is bad. When it gets too low, the organisms suffer. And you can see a band there along the coast that results in quite a bit of invertebrate die-offs as well as changes in the fish assemblages. So I want to do a very simple thing rather than plot the data and making a Hope-Muller diagram and showing you a statistical technique. I'm just going to explain what we think this means for the future. So I'm just going to take what we call the source water, that deep water that's come across the North Pacific. I'm going to take its value of oxygen and I'm going to ask what's going to happen to it when it goes up next to shore where our fisheries are. So looking from the source water to shore. And then I can make a graph like this. On the left-hand axis is the likelihood of hypoxia. That's when the animals are going to suffer. And on the bottom axis is the amount of oxygen in the water measured in milliliters per liter or micromoles per kilogram. So what we're going to see is that for the present time, we have about 25% chance of there being hypoxia on the shelf. Now, as we warm the planet, we're warming the surface of the ocean. And we're actually slowing down the basin scale ocean circulation. Both of those two things are causing there to be less oxygen in the deep ocean. We're deoxygenating the planet ocean. And if we take the projections out to 2060, we're going to have the appearance of these hypoxic zones along our coast about 90% of the time. So it's really incumbent on us to make these measurements, much like all of you have in the atmosphere, but do it all throughout the world's oceans and to get this into the hands of the decision makers. Just a couple of last comments. We've launched the Ocean Observatories Initiative, where this is the largest civilian investment in oceanography in the US. And it's about $400 million, which I think is about the size of one of your guys' cheap, faster, low-cost missions, right?
Yes.
So we hope this does the same thing. I mean, we've seen some great discoveries by your guys' missions. We hope the same from this one. It's an array of instruments across the coast, and we've literally just deployed this in the last month. So I'll just end by connecting this back to planet ocean. Right? Should it really be called planet Earth?
Oh.
It's planet ocean. And there are other oceans out there. So this is why one of the reasons why we're doing this. We're getting all this experience with the robots in our ocean. So we're ready for this mission to perhaps Europa or elsewhere. So thank you very much.
Great talk. Questions?
What does one of your missions cost?
So that robot is about $200,000. And when I go out in a large research vessel, as the alternative, it's $25,000 a day. So if you do the math, somebody do the math, is that 8 days? I can make up the cost of one of those. Now, all you guys know, the money is not in the equipment, it's in the people. Again, I'm sure that's something that Dad knew. It's to invest in the people, and you multiply by 10. So to keep something going like this is $1 million a year enterprise.
You mentioned the role of the heating of the surface water. What about the acidification? What is that doing to the oxygen?
So they're coupled. So photosynthesis, right, takes CO2, makes oxygen. And the other side of the equation, Mary said, don't use any equations. This is my equation. And the other side is respiration or decay, right? That takes oxygen out and produces CO2. So in the same exact process that we're lowering the oxygen, we're cranking the CO2 up. That acidifies the water. What that does is causes any organism that uses calcium carbonate in its skeleton or shell to suffer, especially at the baby stages, the early life history. And so we've seen oyster larvae failures, and there's a marine snail about this big that's starting to have its shell corroded. And those turn out to be what we call the potato chips of the sea. They're eaten by salmon and just about everything else.
One last question for Jeremy.
Can these robotic submarines, or whatever you want to call them, also do measurements like on internal waves in the ocean?
Yes.
And control some of how the wet stuff
Yeah.
goes up and down.
So, again, another story about my dad. Sorry, Scott. When I was at MIT studying all this stuff, he would always come and ask me things like, what do you know about vertically propagating gravity waves? Or another year later, it'd be, what do you know about ship's waves? And I finally figured out, because he was trying to figure out things in the atmosphere or things crossing bands of the planetary rings. So yes, we can measure a number of things, internal waves that are sloshing the water up and down and doing the mixing. And I'll be happy to show you that in that plot. It went by too quickly, but we measure the internal waves.
Real quick.
Since nitrogen has played a prominent role in today's discussion, what about the fertilizer runoff, say from the Mississippi up to New Orleans or from Eastern Asia? How has that 1% area, how has that changed during the last couple of decades? Are things being controlled, that it's decreasing, you know, that zone out of the Mississippi Delta, or is it enlarging?
So when we talk about hypoxic zone, there's two kinds. There's one where there's river runoff with excess nutrients, nitrogen. Chlorophyll blooms robs the oxygen out of the water. The part I'm looking off Oregon is not caused by that. We don't have any pollution or runoff going into the ocean. It's all caused by nutrient supply from below and changes in the open ocean. The dead zones off the Mississippi are in the hundreds across the world. There's 400 of them. And those are getting worse over time as we dump in more and more runoff. So the way you want to think about it is there's the runoff-driven one, and then this more global climate change that's happening. Let's talk more at the Boulderado.